We're going to continue our overview of Java's key functional programming concepts and features by focusing on the need to avoid side effects in modern Java programs. We'll do this by minimizing or ideally eliminating state changes and the use of mutable shared state. And we'll demonstrate these concepts in the context of a buggy case study that will end up multiplying and computing factorials incorrectly in a pool of threads. And you can find this particular example in the EX2 project in my FP folder in my modern Java GitHub repository. Shared mutable state is actually quite common in imperative object-oriented programs. State is data that maintains its value over time. For example, here's a class called total that contains a field called mtotal of type big integer, which is an arbitrary precision integer, and it's going to maintain its state over some time, starting with the initial value of 1. State is mutable if it can be modified. In other words, if it's reassigned after it's been initially initialized. As you can see here, mtotal was given the initial value of 1, but then there's a mult method that takes a parameter n, and it multiplies mtotal by n, and then assigns the value, the new updated value, to the mtotal field. So it's reinitializing it, reassigning it. State is shared if multiple parties can access and or modify it concurrently. Here's a simple example where we have a pool of threads, and several of those threads are simultaneously calling mult on the same instance of total, and those different calls will end up accessing and modifying the value of mtotal concurrently. And as you can see by the name of the link at the bottom of the slide, shared mutable state is considered to be the root of all evil in concurrent and parallel programs. Functional programming discourages state changes and shared mutable state to avoid various types of hazards. One of the hazards of using shared mutable state is that understanding the effects of a method that uses shared state requires knowing the entire history of every shared variable that method uses or affects. Another hazard of using shared mutable state is that changing the order in which methods are called can cause One of the hazards of using shared mutable state is that understanding the effects of a method that uses shared state requires knowing the entire history of every shared variable that method uses or affects, which can quickly become tedious and error-prone in a complex program. Another hazard of using shared mutable state is that changing the order in which methods are called can cause cascading failures because you have dependencies on ordering, which is also very tedious and error-prone to detect and to remedy. We're now going to explore an example of some hazards that can occur when shared mutable state is used in a modern Java program. Shared mutable state is particularly problematic in parallel and concurrent programs. So we'll take a look at an example that incorrectly computes the factorial of a parameter n using a Java parallel stream. And this example can be found in the EX2 project in the FP folder in my modern Java GitHub repository. The problem here, of course, is that we're defining mutable state that's shared between threads in the common fork join pool in a parallel stream. If you take a look, you can see that the mtotal field of type big integer is defined in the total class, and then a single instance of that total class is defined as a local variable inside the factorial method in the buggy factorial class. And the problem here is going to be that we have one instance of total that's then shared between the different threads in the common fork join pool, and the operations that invoke the mult method that will modify the mtotal field in the shared mutable state object total. Let's take a look at how the program actually works, and then we'll see why it's got some problems. It starts out innocently enough, generating a range of values from 1 to n using the long stream ranged closed factor method, which is essentially a functional for loop. We then use the parallel operation defined in the streams framework to run all the subsequent computations in parallel in the context of the common fork join pool. So what that means in this case is we'll have the map to obj intermediate operation convert each of the longs to the corresponding big integers in different threads in the parallel stream. And that's not really a problem because there's no shared state there. However, The for each method, which is the terminal operation of this stream, is where the problem arises. The for each method, as you probably recall, is a terminal operation that has all the other parts of the stream run and then performs some side effect action, which in this case is to call the mult method on variable t of type total. And if you go and take a look at what the mult method does, it multiplies the mtotal shared field by n, which is the parameter passed in. The problem here is that there's one instance of t that's shared within all the threads in the common fork join pool. So those different threads will be calling mult at the same time, which will be accessing and updating mtotal in an unsynchronized way, which of course will cause what are known as race conditions, which are hazards in concurrent programs and parallel programs where the program will behave incorrectly depending on the scheduling order or the timing of the threads. There's another subtle problem here as well having to do with memory visibility, where the mtotal field is then returned as the result, but that itself is not protected by any form of synchronizer, so we could have issues with the memory not being visible from one cache to another in a multi-core processor. That's an even more subtle problem, but a problem nonetheless. Now, the thing to remember about this is in Java, even modern Java, you are responsible for avoiding these kinds of hazards. The Java compiler won't save you, the Java virtual machine or execution environment will not save you. You might be saved if you were to use some third-party analysis tools, either static or dynamic analysis tools that look for race conditions in concurrent programs, but you're responsible for making the right choices. And the right choices, of course, will be what we'll be covering in later lessons in later parts of this material, where we'll be applying more sophisticated forms of synchronization mechanisms and basically reduction mechanisms to be able to work around the issues of shared mutable state and all the problems and hazards that arise when you use it in concurrent and parallel modern Java functional programs. So that's the end of our discussion, where we went into a little bit more detail about yet another key functional programming concept, which was avoiding side effects by minimizing or ideally eliminating state changes and the use of shared mutable state.